So let's talk about contingency tables now. Now, one thing I do want to point out before we leave 11.2 is your expected counts aren't always equal, and then you would put in the proportion that you should expect. And you should be able to figure that out on StatCrunch as you go through. So let's go ahead and talk about contingency tables. Now, contingency tables help us to look at compare if two categorical variables are dependent or independent. Is there a relationship between them, or is there not a relationship between them? And so we're going to look for categorical data that's arranged in a table and it has at least 2 rows and 2 columns. And we're going to look to see if those variables are independent of each other. So, by the way, we are only going to do part 1. We will not be doing part 2. So, we have a table that has 2 variables, 1 row variable and 1 column variable. And every contingency table has at least 2 rows and at least 2 columns. And so we want to see if there's a relationship between them. If there's no relationship, they're independent. And again, O is the observed frequency, E is the expected frequency, R is the number of rows, and you don't include the labels, and C is the number of columns, and you don't include the labels. What has to happen? Again, has to be randomly selected, that they're represented in as frequency counts. Now again, this is where we have to have our expected frequencies are at least 5. Not the observed, but the expected. If all expected frequencies are not at least 5, then you need to combine categories. The appropriate hypothesis is going to be that the row and the column variables are independent. The alternative hypothesis, the row and the column variables are dependent. And again, here is our test statistic. This should look kind of familiar. So observed minus expected squared divided by expected for each cell. And then for each cell we add them up. Now here is the difference. Our expected counts are the row total times the column total divided by the grand total. And basically what this does, it takes your probability of being in that cell, it calculates it as you get your expected count. First thing we need to do is find degrees of freedom, and we can again find a critical value. Your degrees of freedom are your number of rows minus 1 times your number of columns minus 1. And again, these are always right-tailed tests. We're going to be using software to give us p-values, so you don't need to worry about practicing in table A4. Now remember, we can't do cause and effect with this. We can only look at a relationship. Now this is why this works. You don't need to understand it. It all boils down to this. So we are going to look at this. We're going to look at in a couple different ways here just to examine the data. So the first data we're going to look at is we're going to look at how how people who've had heart attacks assess their own quality of life, and we're going to look at some categories there. So quality of life has 1, 2, 3, 4, 5 categories, and then where they live is 2. So we have at least 2 columns and at least 2 rows. And you can see what we've done is we have summed up the columns, and then we will be summing up the rows. So as we look at this, man, oh man, the people in the United States feel a lot better than the people in Canada. But look, there's about 7 times more United States citizens here than Canadian citizens. So we need to do something to standardize it. To standardize it, what we're going to do is we are going to change that into percents. So what I've done here is I have taken those Canadians and divided by the total to get percents. And we look at percents, especially in these first 2 categories, top 2 categories, there isn't much difference. But when we start looking at about the same, somewhat worse, much worse, there is a little difference. So that's worth investigating. Now we can look at those conditional distributions, the distribution within the condition of being from Canada, within the condition of being from the United States, and we can do some comparisons. And we can look at if there's an association or not an association. Let's go back to that data and let's actually use the data and let's do a chi-squared test. This gives you information about the conditional distribution. If the 2 distributions are nearly the same, there's not an association. If there are differences in there, there will be an association. The next slide is some data from another study, and this is data where we looked at education level for French men versus how much they smoke, and you can see we have 3 levels for education: primary school, secondary school, and university, and we have 4 levels of smoking: non-smoking, former smoking, moderate smoker, and heavy smoker. And if you were actually doing a study, you would define these very specifically. So the first thing we need to do, if this was the data that we were given, is we would need to go ahead and calculate the row and the column totals. And that's what I've done. And I also took some time and did percent of the gentlemen who were in primary school and looked at that conditional distribution. The same thing with secondary school and the same thing with university. Again, these are our hypotheses. In the last example, I looked at, I just said dependent, independent. You can say it like this: all the percentages are equal, or you can say they're all not equal, or there's no real relationship in your null hypothesis. There is a real relationship. That's what we need to do as we go forward. Again, here's an example of another null hypothesis for our healthcare study, and we would look at the differences in percentages, but it's multiple comparisons and this becomes very difficult. If we would do this, we would do 2 steps. The first one is we're going to do an overall test to test for any differences, and that's what we're going to do right here, and that's what we're doing with our chi-squared test. Then if this were a study that you were doing, you would do some follow-up analysis to see which parameters are different and how large those differences are. So we're only going to look at step 1. Here is our hypothesis. No real relationship between the two categorical variables that make up the rows and columns in the two-way table. And so we're going to compare the observed counts to the expected counts. And when our null hypothesis is true, we would expect our expected counts. And this is how we do it. Row total times column total divided by table total or grand total. So in our study here, we're going to go through and we would take 616 times 311 divided by 2476, and we'll get our expected count for the number of Canadians who feel much better. And that's how we get our expected count is 77.37. And we would do that for all of our counts, and we would get expected counts that looks like this. Then we're going to compare the data to see if it supports the null hypothesis. So remember our chi-squared statistic. We take our observed minus our expected squared divided by our expected, and then we sum that in every cell of the table. Here's some important ideas about the chi-squared statistic. It's always 0 or positive. The only time it's 0 is when the observed counts are equal to the expected counts. Large values of chi-squared are evidence against our null hypothesis. And the chi-squared test is actually a multi-sided test, so any violation of our null hypothesis gives us a very large value of the chi-squared statistic. So here's that data again. We're going to go through, we're going to calculate our chi-squared statistic at 11.725. When our p-value is less than alpha, or our chi-squared statistic is greater than the critical value, then we know there's a significant relationship that exists. And we can look at which conditions contribute the most to the chi-square statistic by keeping track of the values for the cells. And here is a printout using that, knowing that we have, here's our expected value and here are the pieces of the chi-squared statistic. We have our chi-squared statistic is 11.75 and our p-value is 0.020. Again, our chi-squared distribution is a family of distributions, and the distribution varies by how many things you're looking at, so that's why we look at degrees of freedom. As degrees of freedom go up, our distribution gets more and more normal. When we want to find our degrees of freedom, it's the number of rows minus 1 times the number of columns minus 1. And we can use the chi-square table to get a critical value, or we can estimate a p-value, but we're going to use StatCrunch. So this is a significant relationship between the quality of life and the country you live in. So I've put my data into StatCrunch, and I'm going to go to Stat, tables contingency. Now this is very important. When the data in StatCrunch looks like a table, then we want to go with summary. And our columns are going to be Canada and USA. And you just hold down the Shift key to click more than one. Our row labels are in quality of life. If you want to do your percents, that's fine, but I'm going to do let's do the expected count, and let's do the contributions to chi-square. I want to do a chi-square test for independence. And I think I'm ready to compute. So here what we have is we have our expected values are our first numbers in the parentheses, and then our contributions to the chi-squared statistic is in the last number in the cell. Now remember, to get those expected values, we would have taken the row total times the column total divided by the table total. And that's how we got 77.37. But the wonderful thing is StatCrunch does it for you. Let's go ahead, and I want to snip my chi-square test out of here because we're going to be using that in the next step. So that's how you do it in StatCrunch. Let's go ahead and do a 6-step test. So step 1, quality of life is independent from where one lives. That's going to be our null hypothesis. Our alternative hypothesis is going to be quality of life is dependent on where one lives. So step 2, let's let alpha equals 0.5. And step 3 is where we would put our table in. So I'm just going to put table of data. Step 4 is actually where we do our chi-squared test, and that's where I'm going to paste in my results from StatCrunch. So there is my data. I have my chi-squared statistic, my p-value equals 0.0195. My p-value is less than alpha. So this is statistically significant. So step 5 is going to be reject whole. Step 6 will be these data, or this study suggests that quality self-reported, let's do that, is dependent on where you live. There's our 6-step test. Let's look at this data set of Frenchmen and looking at the relationship between their education level and their smoking level. And what we're going to do is we're going to quickly go through how we would do the chi-squared statistic by hand. And so the first thing I want to do is I need to find the expected count. So I'm going to take the row total times the column total divided by the table total. So I'm going to take 187 times 146 divided by 459, and that's how I get my 59.48. I've done that for all of the 12 cells. And then I need to find my chi-squared statistic. So remember, that's going to be my observed count, the observed count, which is the dark blue, minus the expected count, which is the bright blue. That difference is squared, and then I divide by the expected count. And I'm going to do that for each of the 12 cells. And then the last thing I'm going to do is I'm going to add all those up. And when I do that, I get a chi-squared statistic of 13.304. Let's look at our 6-step test. And so all the P's are equal. There's no relationship between smoking and education level. Not all P's are equal. There is a relationship. Set our alpha level. We can do our data table and just see table for data is okay. In step 3, we calculated our degrees of freedom and we found our critical chi-squared statistic. Here is our chi-squared, the value. I'm going to stop here and let's go out to StatCrunch and let's see how to get this far in StatCrunch. So I've put my data for the education level versus a smoking level. I'm going to go up to Stat, Tables, Contingency, and because this looks like my two-way table, I'm going to do with summary. And my columns are going to be non-smoker, former smoker, moderate smoker, heavy smoker. My row labels are in education. I want to display both the expected count and the contributions to chi-squared, and I'm going to do my chi-squared test of independence. I'm going to click compute, and here is the data I have, and it looks just like what we had on the slide. The only difference is on this table we actually have our p-value directly. So let's go back to our 6-step test and remember our hypotheses, set our alpha, we have our table, we get the same, and then at this time I can either compare my calculated chi-squared with the critical value, or this is where I would put in my p-value, and we found that our p-value is 0.038, which is less than 0.05, so that we get the same conclusion that if we use the critical values. So we're going to reject Ho, so we can say this study suggests that there is a relationship between smoking and education level in French men. Now, remember your you can reject Ho when table. And the one we are going to concentrate on, this first one. When your p-value is less than alpha, you can reject Ho. All of these others have to do with critical values that were much more important before we had easy access to technology. And here is another printout for our smokers, and I'm going to say our differences were in rounding error because this chi-squared is exactly the same as the one that we found with StatCrunch. We are looking at independent simple random samples from several populations, like the Canadians versus the Americans, or we're looking at one simple random sample and then each individual is classified by two categories. That's what happened with the French men. We looked at both their education level and their smoking level. There are some requirements here. Again, no more than 20% of your expected counts can be less than 5. And they need to be 1 or greater. If that doesn't work, then you combine categories. So you might have an other category. This is a test of proportions, but we're testing more than 2 groups. If we simply had a 2 by 2 table, that would be exactly the same as a z-test, a two-tailed z-test of proportions, and that's from chapter 9, not 19. And so they will give you identical results. But the chi-squared test allows us to test more than 2 proportions. That's why we would use that. If all you're going to do is do 2 proportions, use the z-test because then you can do one-sided or two-sided tests. And with the chi-squared statistic, we cannot do that.